Jai Hind everyone. I Neeraj Sharma, Assistant Professor EC Department at Akgec Garg Engineering College, Ghaziabad. I am before you to present the video lecture for the complex topic series for the subject Digital Signal Processing. Subject code is as per the AQT curriculum BEC 503. So in this lecture I have chosen the topic name, that is the IIR filter design by Impulse Invariant Method. This is a top video. This topic will relate the unit number 2 for the subject code BEC 503. Because of this unit 2 is basically dedicated to the IIR filter designing. In the first unit will focus on to the we can say that onto the realization, how we can realize the any IIR filter or FIR filter. But while we will design process which is mentioned for the IIR filter, that is nothing but the IIR is infinite impulse response filter. So for these filter designing, how we can design these filter. So the process regarding the designing of these filter will be discussed in this lecture. So in this series or in the continuation of the topic, the IIR filter, that is IIR means what? Infinite that is infinite impulse response filter. The designing techniques for these type of filter IIR, also we can design the FIR filter, but it will be can be discussed later on. So the infinite IIR filter design techniques are the approximation, derivative, impulse invariant transformation and the bilinear transformation. These three are the more popular techniques for the designing of the IIR filter. So in the here we are discussing with this infinite impulse response, infinite impulse invariant transformation method, which will I have discussed how with the help of this infinite impulse invariant transformation, how we can design the IIR filter. So for this IIR filter design impulse invariant method, so in this technique the desired impulse response, that means what? H of n, which is nothing but the ratio of the output to the input. So the desired impulse response of the digital filter is obtained first by uniformly sampling the impulse response Hn of the equivalent analog filter. So the analog filter which has been given, its transfer impulse response will be notation for that response analog filter given by symbol H of n. So just we are doing its what we are applying the sampling in time domain. So with the help of that means n will be converted HA of n of t. So this will give the equation first, this will give the uniform sampling of impulse response, where the t, this capital T which I was going to use here, that is the sampling interval here. So on the basis of this t, value of t, the sampling is now performed. So the transformation technique can be well understood by first considering a simple distinct pole case for the analog filter system function, which is given as HA of S is equals to summation of I is equals to 1 to m AI upon AI upon S minus of Pi. With the help of this transfer function, we are considering a distinct pole case where the pole is located at the position Pi. The pole value is, when we equate the denominator S minus Pi equals to 0, the value of S will become Pi, which is equivalent to the pole of this corresponding transfer function of analog filter. So, the impulse response of the system specified by equation 2 can be obtained by the inverse Laplace transform, and it will be in the form. So, we have just here the inverse Laplace of this equation 2 will be equals to H A of t is equals to summation of I is equals to 1 to m A I into P I t U A of t. So, where this U of t the unit step function in continuous time here. Now, after that we have to convert this is in a continuous time function. Now, we have to apply the impulse response H n, which we response of H n of the equivalent digital filter, that is what digital filter, and this we are get here for the analog filter. This is the response of analog filter. Now, the response of the digital filter is obtained by uniformly sampling H A of t, that is what, by n applying equation 1 corresponding this one H A n is equals to this one H A n of t. That means, in the equation 3 just we are t will replace them n t. So, summation H of n is equals to summation I is equals to 1 to m A I into e raised to power of p I n t, that is the sampling function with u a n of t, along with these two t here replaced with n into capital T, which will performing the sampling. Now, this will noted as an equation number 4 here. So, what will happen after the system response of the digital system of equation 4 can be obtained by the taking the Z transform. Z transform of this above function can be performed. So, the Z transform will given by this equation H of Z is equals to summation of n is equals to 0 to infinite H n into Z raised to power of minus n. So, after that, now what will happen here, that the value of this H n is now applying onto this equation H of Z is equals to summation of n is equals to 0 to infinite H of n Z raised to power of minus n. So, what will happen? Now, this operation is performed here, that is H of Z is equals to summation of n is equals to 0 to infinite. Now, we have put the value of H n is what, summation I is equals to 1 to m A I into e raised to power p I n t u a n of t. So, the value will be put it here now into Z raised to power of minus of n, which you can see here, or clearly you can visualize it is n is equals to 0 to infinite summation of I is equals to 1 to m A I e raised to power of p I into n into t minus n, this one. So, it can be visualized very clearly, the transformation. Now, we will check it, the analysis, how we can, so this function of this the function h n can be evaluated or converted into the digital domain. So, for that point of view, for the solving, the H of Z interchanging the order of the sign, these two signs can be now interchanged here accordingly. So, summation I is equals to 1 to m summation of n is equals to 0 to infinite A I p I n t u a n of t into Z raised to power of minus n. So, when we will go to the when we will perform its the Z transform, this result will equal to, that is H Z is equals to summation of I is equals to 1 to m A I upon 1 minus e raised to power p I t Z inverse. So, this will be the value of this overall Z transform of the impulse response of H n, which is given by this function, which is equals to H n of Z is equals to H of Z, which is equals to summation of I is equals to 1 A I upon 1 minus e raised to power p I t Z inverse. Now, this response is equivalent to the Z transform of function h of n. Now we will compare this equation 6, which is noted here as an equation number 6. So you can see here, like, compare with this transfer function, original transfer function for the analog filter, which is in S domain, that is ai upon s minus pi. Now these two equations is now going to compare here. So for the comparison, equation 2 and 6, the mapping formula for the impulse invariant transformation, that is we are doing the performation of the impulse. So 1 upon s minus pi is equals to 1 upon 1 minus e raised to power pit z inverse, which you can see here, this part. If we see along with this coefficient a, when we are equating this, so 1 upon s minus pi is equals to equivalent to 1 upon 1 minus e raised to power of pit. So this will be the transformation of the any analog filter with the help of impulse invariant technique, because all the operations which is performed here onto the impulse function. So when we will apply this, though this transformation will S domain when converted into the Z domain. This is in analog response, and this one is your digital filter response. That means the same function, when we are converted into digital filter by impulse, then 1 upon pole will be converted into in the digital domain by this function 1 upon 1 minus e raised to power pit z inverse. Now this is simply a conversion from S to Z domain. Now what about its frequency transformation? How the frequency will be going to convert? When we will say, for that point of view, we are considering its S-plane representation of poles as well as into the Z domain. So for that point of view, we are using the top name relation between analog and digital poles here. So 1 upon s minus pi is equals to 1 upon e raised to power pit z inverse. So it is simply a relation. So here the pole s minus pi, and for the distant this one. Now the analog poles and the digital poles are related by the relation here. We can now just simply considering that z is equals to e raised to power of s into t here. So when we put this value, so these two values will become equal. Okay. So now after that, the general characteristics of the mapping, which depending upon to the function z is equals to e raised to power s into t, can be substituted when we will substitute its value of s for the Laplace domain. The s will represented by the sigma plus j ohm. Sigma, that means this s function, the Laplace function having the real and the imaginary coefficient, when the imaginary coefficient is corresponding to the frequency response, which will represent the frequency of the system. So s is equals to sigma plus j omega n, and expressing the complex variable z in the polar form is equals to z is equals to r into e raised to power of j omega. This will the representation of s. How the s can be a complete value, and the z value will be given by this function r. So when we will compare these, so r into e raised to, put all these values here. So r into e raised to power j omega is equals to what? When we put in this equation, when we put the values r into e raised to power j omega is equals to e raised to power s value sigma plus j ohm t. So we can write it here, r into e raised to power j omega is equals to e raised to power sigma t into e raised to power j ohm t. So here this will represent the magnitude part, and this will represent the j ohm represent the phase portion, phase part. So comparison, we can get that r is equals to e raised to power sigma t, and the frequency transformation, if we see the frequency response of any digital filter is equals to ohm into t. That means when this frequency of digital filter equivalent to the analog frequency multiplied with the sampling interval, ohm is equals to ohm t. So this is the now main basis. With the help of, we can check the mapping of poles mapping of poles from S to Z domain. So for that point of view, we are considering this pictorial view. So where the mapping of the j ohm axis, that means from analog to digital filter conversion, the mapping of j ohm axis is not 1:1. That means there some maybe why? That means when the frequency position is this one, we shifted to the some specific from one position to the specific position. This is not going to perform here. So for that point of view, we are just look for this pictorial view here, in which the first one that will represent the S plane view of S plane mapping of the filter. This is the Z plane. So where you can see that the sigma j omega axis, that is the left half S plane, that is the right half S plane. So ranging from minus pi by t to because value of ohm is omega is equals to what? Ohm t. So frequency here we can see that omega is equals to, that is minus of pi by t to pi by t minus 3 pi by t to 3 pi by t. With now when it is now transformed onto the digital filter, that is in which plane? It is now we are transforming into the Z plane. So here you can see that if the value of sigma is less than 0 equals to what? R is ranging from 0 to 1, means from this one part, this part. When sigma is greater than 1, then R is greater than this part. Sigma is equals to 0, that means where we have R is equals to 1 on to this position. This means this position will convert it into the this position. So when we will the stability of the filter related to the location of the poles, for a stable analog filter, the poles should lie into the left half of the S plane. That means the stable digital filter, that the poles should lie inside the unit circle in the Z plane. This is the condition for the stability. While we can check for the frequency response. What about the frequency response? As in this conversion you can see here. So for that point of view, the statement, the mapping omega is equals to ohm t implies that ohm will be ranging from minus pi by t to pi by t, map into the corresponding value of minus pi to pi. Further, the frequency interval pi by t for ohm is greater than equals to pi by t but less than 3 pi by t, also maps into the interval minus pi. In general frequency, this one is also this response, what one? Minus pi by t to pi by t. That means from here to here, that is lying between to the minus pi to plus pi comparison here on this point. When we are approaching to this one, as per the second, pi by t, ohm value from pi by t to 3 pi by t. That means from this to this part, this to this part, if we see the frequency into the interval of minus pi to omega will ranging from minus pi to pi on the same place. Any frequency interval in generalized way, we can say that when ohm is greater than equals to 2k minus 1 into pi by t and less than equals to 2k plus pi by t, where k is an integer value, will also map into the interval of minus pi to pi for the frequency omega in the Z plane. So after that, what is going on? All the frequencies which we are going, that is now going to place onto the same position. That means what? If we see that the mapping of the analog frequency ohm to the frequency variable omega in the digital domain is many to 1. Number of whatever the frequency into the S domain, it is now mapped onto the interval minus pi to pi. That means many to 1 here. So what will be the issue in this? Because of this mapping, many to 1 mapping, which is providing by the impulse invariant transformation, which simply reflect the effect of aliasing due to the sampling of the impulse response. So because of this one, the major issue will arise is aliasing. Aliasing when introduced, that means what? It will simply, if we say that the general condition in this, the mixing of signals will become the loss of information, because here the frequency response will in the aliasing, the two frequency band will be mapped onto each one, that is the loss of the information. So this is not a good sign. So the problem will arise here, that is the many to one. But we can design the filter, but this issue will comes out. So focus on to the reduction, onto the removal of this issue. So some information useful impulse invariant transformation points has been mentioned here. If we are using any pole here, the single pole we have considered, that is the 1 upon s minus pi is equals to 1 upon 1 minus e raised to power pi t z inverse. So the generalized statement for single pole will be here 1 upon s plus I raised to power m is equals to minus 1 to power m minus 1 factorial dm minus 1 upon ds minus 1 upon 1 minus e raised to power st z inverse for the single many poles. After that, if this will be transfer function is given in the form of s plus a upon s plus a square plus b square, the digital transformation by the impulse invariant will become 1 minus e raised to power at cos bt z inverse upon 1 minus 2 into e raised to power minus at cos bt z inverse plus e raised to power minus 2 at z raised to power minus 2. If it is in the form of b upon s plus a square plus b square, because these are some special notations in the Laplace. So that will equals to e raised to power minus at sin bt z inverse upon 1 minus 2 raised to power minus at cos bt z inverse plus e raised to power minus 2 at z raised to power of minus 2 here. So these are some important transformation with the help of impulse invariant transformation method. So we are considering an example how it can be applied. So for that point of view, here written that the convert an analog filter into a digital filter whose system function HA of s is equals to s plus 0.2 upon s plus 0.2 square plus 9. So use the impulse invariant technique, assume the condition that t is equals to 1 second. So what we have to do here, just compare this result, compare it with the standard transformation, that is it is equivalent to upon s plus a square plus b square. Its transformation is equals to what? 1 minus e raised to power minus at cos bt z inverse upon 1 minus 2 minus 2 into e raised to power minus at cos bt z inverse. Z inverse plus e raised to power minus 2at z raised to power minus 2t. Minus 2. So this can be written here. So, and the value of here a is equals to 0.2 and b is equals to 9. Sorry, b is equals to the value of b is equals to 3 here. So we can convert it. So you can use the formula which is going to for the transformation h of z, as discussed previously, 1 minus this one, and a is equals to 0.2, b is equals to 3, and that value of t is equals to 1 second. Now put all the values into this transfer function and we can simplify it, and the final result, that is the response of the digital filter of any IIR system, is equals to h of z, which is equals to 1 after simplifying these values of e raised to minus 0.2 and cos 3. So when we simplify it, the result will come to 1 plus 0.8105 z inverse plus 1 plus 6.210 z inverse plus 0.6703 z raised to power minus 2. So in this way we can design any IIR filter with the help of impulse invariant transformation formulas. So this is now from my side. Thank you and Jai Hind.